let's look into what is a diagonal matrix. So a diagonal matrix is, so I would like to write the definition here first and then ask you what that definition means. The definition is simply something like this. It is a matrix in which Aij will be equal to 0 if I not equal to j, and Aij can be anything. That is the only condition actually, that completes the condition. So this itself is the definition. I don't need to say what will happen for A. I don't need to say what will happen. This is unnecessary. I don't need to say what will happen if I is equal to j. The only thing that I care about is if I is not equal to j, then Aij will be 0. What does this mean? Can you just think for a while? What can this mean? So what was Aij? Aij is the intersection of the ith row and jth column. So if I have a matrix like this, I go to the ith row, I go to the jth column, I take the intersection of these two, and then the element that I come to is your Aij, right? Now if I is not equal to j, then it's 0. What does this mean? This means, I would like to explain this through an example. So let's look at an example here. Let's look at this matrix 1, 2, 3, 0, 0, 0, 0, 0 and a 0, right? So this matrix apparently looks like something which has elements only in its diagonal. Everything else is 0. So let's look at this element. This is your second row first column element. This is your A second row first column element. So your I is 2 here, your j is 1 here. They are not equal, and when they are not equal, your element is 0. You can verify that for anything. You can verify that for this, right? This simply means that other than the diagonal element, all other elements are 0, right? Even some of the diagonal elements can be 0 or non-zero, like that's not the main thing here. The main thing here is the non-diagonal elements have to be 0, which means that, okay, this is your A11, this is your A22, this is your A33, right? But for these elements, the thing that's common is their i's are not equal to their j's, right? So their i's are not equal to their j's, and that is the reason why all of them have to be 0. That's what you mean by a diagonal matrix. And you can see a diagonal matrix looks like something which has elements only in its diagonal, has non-zero elements only in its diagonal. So this completes our discussion on diagonal matrix. Well, before we move forward, I would like you to draw your attention to this important fact as far as diagonal matrix is concerned. A diagonal matrix has to be a square matrix. It has to be a square matrix, right? So we have already seen what a square matrix is. This diagonal matrix has to be a square matrix, because if the matrix is not square, something like this, if we take a matrix of the order 2 by 3, so it has a data here, 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 and here, here, and here. What does its diagonal look like, right? There's no diagonal as such. The diagonal exists only for square matrices, right? So if I take the first row first column element is present, second row second column element is present, third column is present, but third row itself is not present, so I don't have an element A33, right? So if A11 is there, A22 is there, and the third column is there, then third row also should be there for me to have A33, right? Only then the diagonal will be complete. So diagonal matrices have to be square matrices.